Questions. I'd like to introduce our speaker, Mathew Hampshire-Waugh. He's the author of a book. It's the same as this title, right? Climate Change and the Road to Net Zero. And the subject of the talk will be, the talk will be related to this book, as mentioned in the synopsis email. And be talking about our road to achieving a net zero society. So yeah, thank you for joining us, Mathew, and I'll let you get started. Thank you.
Well, thank you for having me. And yeah, we were just discussing a little bit on my my background. So I was originally started out in science. I did a PhD in material science, looking at sort of nanomaterials and energy efficiency glazing and enhancing the efficiency of solar panels. And then I went on to work for Credit Suisse, an investment bank, for nearly a decade, where I was covering the European chemicals sector. So I'd work with senior management, CEO, CFO of large listed European companies, and model those companies, forecast cash flows, and value the shares, and pass on my recommendations of buy or sell to institutional investors like pension funds or hedge funds. But that gave me the opportunity to actually continue my sort of passion into looking into new energy technologies, because chemicals companies are typically key intermediaries within the supply chain. So I looked at lots of things from polysilicon for solar panels to battery materials for electric cars to enzymes for bioethanol, and sort of broadened out through the supply chain. So got a lot of broader learning under my belt there. And then in 2019, I decided that I wanted to go away and write a book, taking my expertise in finance and science and sort of building out into sort of broader economics and politics, because I just thought this was something missing in the book market in climate change. There was nothing that sort of ran through the problem in its entirety and kind of put numbers on everything. And so that's what I spent 2 years doing. Published it last year, a little bit later than I was expecting due to COVID. And then since then, I've sort of had incoming work and set up a consultancy business on climate change and net zero. And today, the presentation, it's going to be on the book. It's going to be high level, very much top down. I'm going to have to move quite quickly because there's a lot to cover. So we're going to take a journey through climate change and the road to net zero. And we're going to run through the science, technology, economics, and politics of global warming and the transition to a zero carbon economy. So let's begin. And I'm going to begin with a brief history of human progress, prosperity, and the role played by fossil fuels in that. So if you think about what's driven human development since our first ancestors 4 million years ago, well, the answer is a virtuous circle of unlocking energy surpluses, which created more time for human innovation, allowing for better storage and transmission of knowledge, which helps to unlock more energy, more innovation, and more knowledge. So you can look at the first cave drawings 50,000 years ago, the agricultural revolution 10,000 years ago, Johannes Gutenberg's printing press in 1450. You can see that this, as the chart shows there, this human development and the virtuous circle have been driving this progress for millions of years. But what we can also see is that for most of human history, more energy and more resources were always met with more mouths to feed. And the average human was stuck at the same quality of life because productivity improvements were linear and relatively slow, whereas population responded exponentially and increased too quickly. And this became known as the Malthusian trap. And this chart just shows that for thousands of years, average incomes were stuck at the equivalent of, in today's money, of about $1,000 per person per year. That is until about 200 years ago with the Industrial Revolution, where we learned to harness fossil fuels to power machines and to supplement human labor, which drove exponential increases to productivity. You've seen a 20-fold increase in average incomes, in energy use, and in knowledge building. So today we don't rely on the direct power of the sun anymore, but we've been able to unlock vast stores of the sun's energy, which has been captured over millions of years by plants, which is then buried, concentrated, and obviously stored in fossil fuels, in coal, gas, and oil. So to give you an example of that, 1 barrel of oil contains 100 tons of concentrated ancient plant matter, and that can deliver as much energy as nearly a decade of manual labor. So fossil fuels have really unlocked the potential of human capital. And we can see how that's changed the world. The number of industrial machines per person has risen more than 200 times through the 20th century. And for the first time in history, we have a sustainably improved prosperity has been made possible for an increasing number of people. So, energy consumption per person, that's increased tenfold. The first academic journal, that wasn't established until 1665. There's now nearly 30,000 academic journals publishing close to 2 million papers every year. And of course, the average income or GDP per person has gone through that $1,000 barrier and has grown to nearly $18,000 per person per year. And the combustion of fossil fuels, mechanization, the industrial revolution, it's completely changed the world. And here are just a few examples. So this chart shows the agricultural employment now accounts for just about a quarter of global working life, from near 100% of life a couple of hundred years ago. Life expectancy, well, that's more than doubled from 30 to 70 years. Child mortality, that's fallen from 43 to 4%. And extreme poverty has fallen from 90% to just 10% today. So what I write in the book is that although it may not always feel like it, we are actually living through a period of unprecedented wealth, of quality of life and peace. So life for your average human being is better than it has ever been. And yet you have to remember that we're a long way from completing our journey because there are still big inequalities around the world. So you can see here a significant proportion of the world's population still spends most of their time laboring in the field, earning little income and isolated from those energy surpluses of the modern world. For many, life expectancies are still short and child mortality rates are still high due to poor diet, lack of access to medicines and professional healthcare. So take a look at this chart. You can see that 1 in 10 children born in areas like the DRC, Sierra Leone, or Mali will die before the age of 5. And to illustrate just the extent of global inequality, which I had never appreciated before digging into it, to make it into the top 10% wealthiest of the global population, you need to earn just over $16,000 per year. And that means that you earn over that, and it means you likely went to school, you drive a car, you've got access to electricity, hot running water, you eat pretty much whatever you want. But for every person that is in the top 10%, there's someone still stuck in the bottom 10% who consumes the equivalent of less than $1,000 per year and remains stuck in the Malthusian trap. So for them, work is done by hand, they travel by foot. Most of the time is spent laboring in the field or walking to the nearest well, as there's no access to safe water or sanitation. And they're still largely cooking and heating their homes with an open stove, which makes it a huge health hazard and makes it incredibly difficult to breathe. So big inequalities remain. And why do we go in? Why do I start here? Well, because the majority of the global population are rightfully striving still for a better quality of life. So of course, global consumption is going to continue to increase. There are going to be more miles traveled, more food eaten, more products made. So we need to not just figure out how we get to net zero from where we are today, but how we get to net zero whilst the global population is still growing and consumption per capita is still increasing. And the chart here just shows that, you know, if we move to a peak population world where everyone can enjoy this is a kind of European or US level of consumption, but we don't change the way that we power the economy, we don't change our energy and agricultural systems, then you can see that, you know, greenhouse gas emissions per annum will go from 50 billion tons to 100 billion tons per year if we made no systems change from where we are today. Of course, that's, you know, there are changes taking place. This just gives you a sort of baseline of inaction. And in the next section, I just want to run through what this baseline of inaction, what impact it will have on the climate and on Earth's systems. So why do greenhouse gas emissions matter? And why does carbon dioxide act as Earth's thermostat? And so it all starts with our relationship with the sun. So the sun's radiation energy hits the Earth's atmosphere with an average intensity of 340 watts of power per square meter. So that's, you know, 3 old incandescent light bulbs per square meter. Atmospheric gases, clouds, snow, ice, oceans, and the Earth's surface, this reflects about 30% of that energy straight away back into space. The remaining 240 watts per meter is absorbed by the atmosphere, land, and oceans. So the portion of the sun's energy which is absorbed is then re-radiated and sent back towards space as lower energy, longer wavelength infrared radiation. Now, water vapor and greenhouse gases like CO2 in the atmosphere are very effective at absorbing outgoing infrared radiation and in turn re-radiate that energy in all directions. And what this does, as a very basic definition, is it serves to trap more heat before it escapes back into space. So it heats the lower atmosphere, which is known as the troposphere, and it cools the upper atmosphere, which is called the stratosphere. So this is the phenomenon known as the greenhouse effect, and that was coined by mathematician Joseph Fourier in 1824. And that was actually a little before the process was fully understood. Now you can, you know, that's the kind of basic definition. You could start getting into the weeds a little bit more on the actual physics of it, because quite clearly, you know, as it creates an energy imbalance, the Earth doesn't just keep heating and heating and heating, or else we would have blown up by now. So if you dig a little more into the physics, you can start to better understand why adding more CO2 to the existing atmosphere creates a warming effect. So firstly, because CO2 is at a relatively low concentration, and this is 280 parts per million CO2. This is where we were pre the Industrial Revolution. The frequencies where the gas absorbs infrared are not fully saturated. So as we add more CO2, we can close off further parts of the atmospheric window where that radiation was escaping directly to space. So this prevents a little extra portion of energy from escaping straight out into space. Instead, the energy is emitted, but it's emitted from a point higher up in the atmosphere, where the atmosphere is colder thanks to adiabatic expansion. And thanks to the Stefan Boltzmann law, which you can see down here, a colder emissions temperature means less energy is radiated. So this is what really creates that energy imbalance. And you can see if you go from 280 parts per million to 560, it creates roughly a 4 watt per meter squared imbalance. And this leads to a warming of the surface of the Earth. And this initial temperature increase allows the atmosphere to hold more water vapor, which again raises the average height of the emissions level where that energy is escaping to space. So you can see how this process creates this imbalance, and it continues to be imbalanced in terms of energy in and energy out until you've heated up this lower portion of the atmosphere here to rebalance the temperature up here. And you can see that this is, and the difference between those two, that's global warming. So going from 280 parts per million to 560 parts per million CO2 in the atmosphere creates that energy imbalance. The surface has to warm from 14 degrees C to 17 degrees C in order to get this point back to temperature and to rebalance the books again. So that's a little bit more of a nuanced, it's a little bit more of an involved take on the physics, which goes beyond that basic sort of explanation of the greenhouse effect, which doesn't quite make physical sense. But in short, adding greenhouse gases to the air partially closes that atmospheric window, creates a thicker blanket of gases, and warms the lower atmosphere of the planet. But how has this effect played out in the past? Well, the chart here shows the relationship between CO2, that's the dashed line, and temperature, which is the solid line, which scientists can now track back 500 million years using rock samples. They can track it back about 1 million years using the bubbles of atmosphere trapped in ice cores, and about 100 years using the direct temperature and atmospheric records. And it shows that if either temperature or CO2 increases or decreases, then the other will follow. So they're both intertwined on this journey. And this relationship has held true since the dinosaurs were roaming the earth. And so, we can see physically, why does CO2 control temperature, and vice versa, why does temperature control CO2? We've seen that relationship, the physical science is there. There is a relationship that's held for 500 million years. And so next we need to ask, well, what does that relationship look like today? And this diagram just shows how carbon today is moving in and out of the atmosphere. So you can see over here, you've got decay and respiration being of vegetation being offset by photosynthesis. You've got CO2 moving in and out of the ocean. And then on a longer time scale, you've got rock weathering and volcanic activity, sending CO2 out and back into Earth's, between the atmosphere and Earth. But this red dotted area here is what humans are doing. So we are releasing 9 billion tons of carbon. That's 36 billion tons of CO2. Into the atmosphere every year. Now, roughly half of that is offset by the land and ocean sink, absorbing a little more in response to the heightened concentrations in the atmosphere. But that leaves us, 4.5 billion tons of carbon off balance. And so there's a cumulative effect where basically carbon is entering the atmosphere and it's cumulatively building up, and it's adding to that parts per million CO2 concentration. And if you look back for the last 10,000 years, those natural processes have been balanced. The flows of carbon in and out of the atmosphere were equal, and this has meant a very stable climate, which allowed for the agricultural revolution and the industrial revolution and all the improvements to human quality of life that we just talked about. But now, we're adding CO2 into the atmosphere faster than any natural event in at least 66 million years. And as we've seen, it's got no natural counterbalance, meaning that CO2 is still increasing. So you can see that CO2 here on a shorter time scale over 2,000 years, it's gone from that very stable 280 parts per million, so 0.03% of the atmosphere, to over 400 parts per million in just 100 years. And that's been accompanied by over 1 degree C of warming so far. And so in short, we're pushing the planet into a state not experienced for at least 5 million years and possibly 50 million years, depending on where we end up. So change is happening. We can explain it. We can map it into the past, and we know what's going on today. So let's just explore next what scientists think is going to happen this century, should we make no concerted effort to further decarbonize the economy. So this assumes where we are today, nothing much changes. It just, the population grows and consumption per capita increases through the next 80 years. So this is kind of our baseline. And by the way, this isn't new science. So it's science which is 150 years old. So it was first figured out by Eunice Newton Foote, who was a women's rights campaigner who first linked Earth's temperature to CO2, but was ignored by history until very recently, basically because she was female. And if we look to the earliest computer-based climate models, which were put together in the 1970s, and one of the original pioneers of those computer models, Manabe, has just won a Nobel Prize for his work. Well, actually, they've been incredibly accurate. So you can see the wiggly line here, that's the actual temperature record. The other three lines, well, these are the temperature predictions made by Sawyer, Broca, and Hansen, 50 years ago. And they pretty much tracked spot on. And now, of course, we have supercomputers working to run these climate models, which have become ever more complex. And the IPCC, the International Intergovernmental Panel on Climate Change, kind of takes these simulations, aggregates them, and shows the likely outcomes under different scenarios. So if we look at the scenario where we move to peak population, peak consumption world, which is still powered by fossil fuels, then CO2 roughly will increase from 400 parts per million today towards about 1,000 parts per million by the century's end. So this is an emissions pathway called SSP 3-5, or there's an even more extreme one called RCP 6-8.5, but this one's looking rather unlikely because it would require large use of coal to chemicals and coal to liquid fuels, which the world has moved away from in the last 10 years. But the outcome is that temperatures increase by at least roughly 3 degrees C, and expanding water, melting ice sheets will raise sea levels by nearly 1 meter. So humans have never existed in a climate like this, basically. So this all sounds bad, and I don't want to be a harbinger of doom, but we need to look at what it means in terms of physical, social, and economic change. So let's take a quick look at some outcomes. And this is a chart that I put together that just shows the cumulative impact on the global population based on scientific estimates of each of the sort of physical effects. So every 1 degree of warming reduces agricultural yields by about 5% beyond 2 degrees, and reduces fresh water availability by about 5 to 10%. So this would create pretty widespread climate-related hunger and water stress in the back half of this century. Plus, you get intolerable sort of heat and coupled with rising seas, and that's going to put nearly 1 billion people at risk of sort of forced migration by the back end of this century. Air pollution, which is often overlooked, and 90% of air pollution is due to the combustion of fossil fuels, and air pollution is already the world's second biggest killer, and that's only going to increase if the use of fossil fuels goes on increasing. And then finally, maybe the ones that make the headlines more often, the climate-related natural catastrophes, things like wildfires, heat waves, storms, hurricanes. The frequency of those have already tripled. Another 2 degrees warming, and they're going to triple. They most likely will triple again. But you can see they may be the headline grabbers, but it's really the forced migration, the water stress, the hunger, those kind of long-term issues that really build and really affect the most people. But by the century's end, about half the global population could be severely impacted in one way or another by the effects of climate change. So if we map this onto global incomes, so we can look at how this will affect capital equipment, how it will affect productivity in the labor force, and you work these those impacts through. It could destroy around 10 to 15% of future incomes, that black line here, which when you convert that into today's money, because we have to account for increasing wealth in the future, it's about the equivalent of losing 5% of today's GDP. And that's shown by the dotted line here, using a standard discounting equation. So that's roughly $4 trillion of economic losses from damaged buildings, equipment, lost productivity, and disruption through this century, thanks to climate change. And that places, put this into perspective. It sounds like a big number. Is it a big number? Well, it puts climate change in the top 3 of global economic spending issues, behind fraud losses and the amount that we spend on healthcare around the world every year. And if we include air pollution, which I think should be rightfully bundled up with climate change and CO2 emissions, because 90% of it is due to the burning of fossil fuels, then as a combined issue, they take the #1 spot in terms of risk factor leading to death. So you can see here annual deaths per million people, and this is now, and in 2100, should we just let the use of fossil fuels grow? And so it's a top 3 global problem. The world is right to be concerned about climate change, and all of these predictions assume that climate change follows a predictable pathway. But of course, scientists understand that there are physical changes in the Earth system called tipping points, which could actually make these predictable sort of modeled damages way worse. These are things like a breakdown of the ocean circulation current, which controls a lot of the world's weather, dieback of the Amazon, because as it heats up, it's got its own sort of microclimate, which is lost, or shifting monsoons, which would dramatically impact Africa and areas like Pakistan and India. And then there are the socio-economic tipping points. What's perhaps labeled the carbon crunch could occur. So this is where the world realizes that, hey, we've got to get rid of all these fossil fuel assets really quickly because of all these physical changes taking place. And that's done too quickly. Those assets have to be written off in terms of value. And the large bubble here just shows the carbon crunch, the potential economic write-downs in relation to the credit crunch from 2009. And hey, the disruption and the lost wealth of the world could be 10 times bigger if we don't get the transition right. So the combination of predictable damages and unpredictable tipping points tell us that, in my view, we must take action on climate change. But we still need to figure out a strategy. So let's look at a few options here. And first off, we need to know where the bulk of greenhouse gases emissions come from. And luckily, that's exactly what scientists have pieced together over the last 30 years. So Of the 50 billion tons of greenhouse gases that we emit each year, they are evenly split between transport, basic amenities like heating and cooling buildings, agriculture, and industrial production. 2/3 are from the combustion of fossil fuels and is CO2, and 1/3 are non-energy processes associated with agriculture or industrial reactions, and they may not necessarily be emitting CO2. It may be methane or nitrous oxide or halocarbons, but you can put all of this into CO2 equivalents, so the equivalent of 1 ton of CO2 gas, which is what's shown here. So that's the problem, and we need to somehow address it. And we've got 3 basic options. We can adapt, we can look at climate engineering, and we can look at mitigation. So an adaptation only strategy, well, that means making no real change to human systems. We just let emissions grow from that 50 to 100 billion tons per year, and we adapt as the Earth warms, as sea levels rise, and as the weather becomes more extreme. So we could build cooling shelters, bigger sea walls. We can design drought-resistant crops to minimize the damages from climate change. And that as a strategy, well, it's relatively low upfront cost, it's relatively low effort, but it risks unmanageable change, and those tipping points could eventually prove disastrous. We just simply couldn't adapt enough or fast enough. We could try and avoid climate change impacts using climate engineering whilst still burning fossil fuels, by either using negative emissions technology, which draws CO2 back out of the atmosphere, using something as simple as tree planting, or something as complicated as big suction fans, which filter the CO2 out of the air and store it underground. Or we could do it by limiting the energy reaching the Earth in the first place by reflecting sunlight on a global scale. And there've been schemes proposed such as mirrors in space, manipulating or whitening clouds, or adding aerosols to the stratosphere to reflect that sunlight. The problem with negative emissions technologies, which you can see here on the left of this chart, is they're physically limited. So what you can see from the diagram here is that they can cover less than sort of 10 billion tons of CO2 per year, less than about 20% of emissions at most, really. Then the solar radiation management, well, it's a more scalable solution. You know, you can quickly block that heating effect. It's relatively cheap and easy, but it doesn't solve air pollution. It doesn't solve ocean acidification, which is CO2 being absorbed by seawater as the concentration increases in the atmosphere. And it doesn't address a lot of those tipping points. And it runs a huge risk of going wrong and creating accelerated climate deterioration. If it should stop working, maybe it's a political act, maybe it was a terrorist act, whatever reason, the Earth's climate quickly plays catch up with where it would have been based on the concentration of CO2 in the atmosphere. So change is even faster than it would have been. So for me, the only low risk, scalable and complete solution is mitigation, which is where the world is heading. And that says obviously that prevention is better than cure, that we need to eliminate greenhouse gas emissions in the first place, rather than putting a band-aid on the planet. And there are 4 ways to reduce emissions. And the chart here shows the warming outcome of each action in isolation. And this is something called the Kaya identity, which just says that greenhouse gas emissions are a function of population times GDP over population times energy per GDP times emissions per energy. So this just breaks it down into a simple 4-cause basic equation, if you like. And so you can see population control first off. no matter what you do to look at limiting population control on your model, which is what I've done here, it's always going to be slow, ineffective, and actually population will self-limit with global growing wealth anyway. And it's obviously morally challenging to put in population control measures. And ultimately, there's always going to be residual emissions. So population control for me is an absolute no-go. Alternatively, we could limit consumption, or we could improve energy efficiency. But again, neither of those are going to get us to zero emissions, which is where we need to be if we're going to stop global warming, stop that accumulation of CO2 in the atmosphere. So that basically leaves us with net zero technologies to take the emissions intensity, the end part of the equation here, of the energy system and of agriculture. We need to take it to zero. And that's the only surefire strategy. Of course, a mix of all four will help. So, efficiency measures are generally economically productive, and of course buy lots of time. Limiting consumption where it's not detrimental, again, buys time. But the end game is getting that emissions intensity to zero. So what does a zero carbon intensity system look like? I want to start with the energy supply. So our current energy system is 80% fossil fuel, based around coal for electricity, oil for transport, and gas for both electricity and heat. And we need to eliminate those emissions. What options do we have? Well, let's start by reviewing the techno-economic attributes of each type of energy supply. And this chart just shows the life cycle emissions of different energy supplies, including the emissions from running the equipment and the emissions from manufacturing the equipment and processing the fuel. So it's full life cycle emissions. And you can see that wind, hydro, solar, and nuclear, well, they've got 10 to 20 times fewer emissions than fossil fuels today. And once renewable energy is manufacturing renewable energy equipment, that trends towards zero. So, we have credible low carbon options, but low emissions is no good if we can't produce enough energy. And actually, this rules out something like biofuels as a dominant energy supply, because simply we don't have enough land on Earth to make enough to grow and manufacture enough energy from biological sources. This chart also shows you, this is just percentage land required to power all the world on each technology standalone. It also tells you that wind and solar, which are here, provide 10 to 100 times less power per square meter of land compared to fossil fuels or nuclear. So in terms of density, land use, they're a factor out, but you're still just talking 1 to 2% of dry land on Earth to provide all of our energy needs from wind and solar. So far, wind and solar renewables are looking good. So next, we've got to consider safety. And this chart just shows deaths attributed to each unit of energy supply. So each terawatt hour of energy supplied, how many deaths occurred. And it shows you that renewables are far safer than fossil fuels, and that's because they don't produce any harmful air pollution, which, coming back to the fact, it's one of the key reasons for deaths around the world today. And we've all, and interestingly, just to pick out from this as well, so wind and solar are great. Nuclear also looks great. Perhaps something that you wouldn't expect, but it's statistically the safest form of energy historically, despite public perception there. Nuclear, however, falls down on costs. So it's proven stubbornly expensive. Whereas renewables like wind and solar are following what's called a technological learning curve. So every time solar installations double, the cost of solar has dropped by 20%. Every time wind turbines manufactured have doubled, the cost has dropped by 10%. So you've got this learning curve in action. And this final chart just shows the costs of each energy source over the life of the installation. And it shows that the renewable electricity has already reached an equivalent price to fossil fuel electricity generation all over the world. That's the light blue bars. And this is actually based on average prices before the current energy crisis. So this was pre-Russia's invasion of Ukraine. If you look at wind and solar currently, they're about 3 to 4 times cheaper than natural gas electricity. But importantly, if wind and solar again scale up from the 2% of energy they are today to become the backbone of energy supply, let's say 2/3, the installations need to double another 5 times. That means the costs should drop to less than half that of the cheapest historical prices of fossil fuel electricity. That's the dark blue dotted bars. And so they're actually going to be, renewables in the future are going to be competing with coal, oil and gas, not just for electricity generation, but for just heating. And so wind and solar are extremely promising in terms of scalability, safety and cost, and of course, security of supply, as we're all experiencing around the world at the moment with the issues of importing natural gas from essentially a cartel of countries which controls all of these fossil fuel resources. Nobody controls the wind or the sun. But of course, there is reliability. So renewables are, of course, intermittent. How can they provide a reliable energy supply? So we need to look at energy storage next, because it's certainly true that the wind doesn't always blow and the sun goes down at night. And you have cloudy days. So electricity or energy storage is required. And electricity is, well, it's the only commodity in the world which isn't stored and has to be managed in real time. So running an electricity network is kind of ramping up and scaling down generation from all your power plant assets in real time to try and match the demand which is changing through the day, and as everybody puts on their kettle during halftime for the World Cup. And that's crazy. And it's the only commodity in the world that's really run like that. And it's a very essential one. But as a rule of thumb, it's sort of worst case that we don't sort of grid all of ourselves together very well and sort of mesh grid networks in the future. Roughly half of renewable generation would have to be stored on a daily basis, and about 5% of annual generation stored between sort of summer and winter. And you can just see the demand here. This is on a daily basis. That's what demand looks like. And if you had 50-50 wind solar, that's kind of what your output would look like. So you need to store it for later. Same thing between the seasons of year. You get lots of solar in summer, you get more wind in winter. They don't quite match, and the demand changes through the year. So again, you need that longer term storage. But luckily, electricity storage solutions such as lithium-ion batteries used for short-term storage, well, they're falling in price even faster than wind and solar. So they're coming down 30% every time production doubles, thanks to the onset of electric vehicles. So we already have the technology we need. So batteries or pumped hydro offers a solution to daily electricity storage issues. Hydrogen or thermal storage or offer solutions to interseasonal, longer term energy storage issues, and would be used alongside sort of grid interconnections between regions. And if we combine the cost of renewable generation, energy storage, transmission, and distribution to homes and businesses, then still wind and solar will be the cheapest form of reliable electricity supply in the future. So I think they'll provide cheap, scalable, safe, reliable electricity in a net zero future. and with a mix of other technologies to fill the gaps where either the engineering is too difficult or the economics don't stack up. I think electricity is going to go from 20% of all energy to 75% of all energy. But of course, we need to solve the problem of how we use that energy, because it's coming in the form of electricity, not petrol or gas in the tank of your car, or whatever it might be. So what we need to do is we need to electrify everything where possible, and use hydrogen made from renewable electricity, low carbon biofuels, or emissions capture where electrification is not possible. So for transport, this just shows the total cost of buying and running different vehicles. The most economic way to decarbonize transportation is to switch to electric cars and electric short-haul planes and ships. Maybe use hydrogen planes or ships for mid-haul, and use biofuels for long-haul or air travel. For industry, you can see in this chart that the energy use is mostly used for heating processes. So industrial heating must switch away from coal or gas, and it needs to use an electrical load for heating instead. And then you've got direct emissions from things like cement, fertilizer, steel, and there you need either to switch to chemistry or you need to use carbon capture. For amenities, well, this chart shows the buying and running costs of heating options in our homes and businesses, and it shows that switching from natural gas boilers, which are certainly most common in the UK, to electric heat pumps can be done with a slightly higher cost. So we have all of the options out there, and that energy supply and demand needs to switch, but also global food systems need to decarbonize. So agricultural emissions are a little different from the energy system, because only a small percentage of ag emissions come from combustion of fossil fuels. The majority come from agricultural processes like forest clearing, which releases the carbon trapped in trees, peatland draining, releasing the carbon stored in soils, methane from cow and sheep burps, and the release of nitrous oxides from using fertilizer. So improved farming techniques can reduce ongoing emissions to an extent, but the biggest change in farming is going to have to come from reducing land use in the first place. And this chart shows land used for agriculture in a peak food world with different actions. And you can see from this the best way to reduce land use is to reduce meat consumption. So you can see here an all vegan world, and that's because the average diet uses 1 football pitch of agricultural land. The vegan equivalent uses just the penalty box. So it saves a huge amount of land and wasted calories. Another good option you can see from this chart is moving to best-in-class yields everywhere. So the amount of food grown per unit of land. And there's 50% improvements to be found if modern farming techniques can be adopted all around the world. So pulling these levers, we can reduce the need for agricultural land, and we can provide that much needed space for reforestation to trap carbon from the atmosphere. Of course, you're not going to hit any of these extremes, but some sort of mixed, balanced agricultural system can get to net zero. So I just want to finish off with the overall benefits or negatives of moving to a net zero economy. And firstly point out that electrification is multiple times more efficient than combustion. So electric heat pumps to heat your house, they use 4 times less energy per unit of heat than natural gas boilers. Electric cars use 3 times less energy per mile driven. If you start adding this up across the whole system, net zero will actually use half as much energy as the fossil fuel equivalent economy. This means that when you factor in the full scale electricity supply from renewables, the added upfront costs of things like batteries or heat pumps, then the whole system will work out about 25% cheaper. So that to me is the end game. So we have a more efficient system, which actually on a buying and running cost is 25% cheaper than the equivalent fossil fuel system. So if this chart's a little complicated, but what this is showing is that if we know that net zero is the end game and it's cheaper than the fossil fuel equivalent, and that it's not the passing of time that makes things cheaper, but scaling up production, then why are we sitting on our hands and waiting? And so if you factor in things like the time it takes to reskill the labor force, the potential write down of fossil fuel assets, outcompeting other investments in the economy, which will reduce GDP, then roughly on my numbers, it's about a 20-year transition to net zero is optimal. So that delivers $50 trillion more wealth from a cheaper energy system, and it avoids $120 trillion of climate change damages over the rest of this century. It's a win-win for me. So, you know, net zero, it solves air pollution, it reduces resource consumption, it creates a more distributed, equitable energy system. It can bring the bottom 10% into the modern world, improve quality of life for all. We can let everybody live a sort of European, US level of consumption. We can avoid the worst climate change outcomes. We can do it with lower energy costs, stronger GDP growth, and a more sustainable energy system with less price volatility and less reason for international conflict. So, you know, we can stick with fossil fuels and maybe we'll be okay if we adapt, or maybe we'll get it wrong and we'll end up with all those tipping point risks. Or we can push through mitigation, which is the way the world's heading, and we can create more human prosperity for all. So, you know, just to finish off in the last 5 minutes, you know, if it's so great, why have we made so little progress? Why in the 30 years since the IPCC was formed, have we put more CO2 into the atmosphere than all of human history combined? And that's, you know, quite a staggering stat. And there's no simple answer. It's a combination of multiple factors. You know, there's inequality. So this chart shows that the richest countries of the world emit the most CO2, and yet will suffer far less GDP impact than the poorest countries who have contributed very little to global emissions. So the incentive to act on climate change is misaligned. This chart shows the cumulative emissions over the last 200 years versus wealth, illustrating those same rich countries got rich from burning fossil fuels in the past. So the question is, how do we fairly allocate the remaining carbon emissions to limit warming to safe levels? And this is what climate economist Lord Stern called double inequity. And this has been a big feature of the latest COP meeting in Egypt. And then there's self-interest. So, you know, climate negotiations are often likened to the prisoner's dilemma. Why does an individual country take action to reduce emissions when they can't be sure that other countries will act? Self-interest suggests taking no action and waiting for others to pay the higher upfront cost. And this just shows, you know, Europe leading on renewable installations, with the US lagging 5 years behind, which links more broadly into the tragedy of the commons. How do we overcome self-interest and act for collective good? So, you know, we can emit greenhouse gases, which we know inflict damage on others, but we pay nothing to correct our mess. So economists call this an externality. And in addition to that, there's lots of issues within markets which create disincentives. Things like the expense of buying an electric car up front, even though over the life of the car it's cheaper. Or, you know, why should a landlord pay to insulate his property when the tenant takes the benefit? So there's lots of issues, but we also have lots of solutions. And we're overcoming that national self-interest through the Paris Accord, which is not a one-time game of prisoner's dilemma, but a repeating game every year that helps build that trust and push for more accelerated action. And that's working. It's building trust and it's ratcheting ambition. And there are also these market failures. But you know, you can see on this diagram here that we have left-leaning or right-leaning political policy actions, which can address each and every one of those aspects of market failures. So despite, you know, the balance of liberalism or socialism, right or left, you know, governments, corporates, and individuals, through, you know, all of these establishments and through culture, can push and must push together. You know, it's no individual. There's no individual one here that needs to solve climate change. It's all three. And so, you know, that means, you know, to put it in perspective, a 20-year transition requires us to deploy renewables 5 times faster and we need to electrify the economy, talking driving, heating, industry 10 times faster. So we need to get a move on. We need to shift a lot of money. So this is going to be the cost of net zero, $3.5 trillion per year. This is how much we spend today. So all of this oil and gas needs to go into renewables. And then we need to find another 1.5% of GDP to fund this if we are to move fast enough. But those investments will quickly pay back through financial income, improving health, and a cheaper energy system. And through the avoiding the worst impacts of climate change and dangerous tipping points, which we've outlined in the presentation today. So if I can leave you with one message, it's that net zero is a win-win for both the economy and the environment. And I've just about done it in the hour, so I apologize for maybe moving through those slides at the end a little quicker, but I wanted to leave some time for Q&A.